Okay, I think now we are all ready, all set for projections or projectors, as we will often say. And therefore let our space X be given as a direct sum of two of its subspaces U and V. The fact that it's a direct sum means that every little x from X has a unique decomposition. Little x equal to little u plus V into U from U and V from V. Okay, and here's our definition. We call PU, which is a map from X into X, and it takes every little x from X into its uniquely determined U component from U. So we call that operator the projection of X onto U parallel to V. Okay, so there's a whole lot to say here. Projection of X onto U parallel to V. And then of course by just exchanging the roles of U and V, you would introduce the other projection PV, but we don't even have to say that in the definition because it's just, well, V is just another U. But if U and V are complementary subspaces in capital X, which they are if we can write this, then we call PU and PV complementary projections. Alright, we should probably mention that PU also depends on the choice of V. So for example, in this setting, the projection moves that point X down here. Whereas in this setting, with a different complementary space V, but still the same space U and still spanning the same space U plus V, the same point X is mapped to a completely different projection. So even though we are not putting the set V as a part of this notation here, because we're trying to keep our notations slim, it does depend on V, and it is not without a reason that we say parallel to V in this definition here. Right. Okay. So if someone's asking you what is a projection or what is a projector, then you could tell them the same story of the last 20 minutes that I was telling here. Or you could give them this alternative definition. A projector is a linear map P from X to X with the following property. It holds that P squared equals P. Definition is finished. Now, is that indeed equivalent to what I was saying in the last 20 minutes? Well, we will see that it is. So let's call this the geometric definition, because it's speaking about the subspaces and how one together with the other spans or gives you the whole space as a direct sum. And let's call that one the algebraic definition, because all it's saying is this little algebraic equality here. And I think it's easy to see that the projections that we defined in the geometric definition are subject to that equality P squared equals P from the algebraic definition. Because if you take your point X and you project it down to its U component, then you've applied the projection once, and if you apply it again, so you take that little U and try to split that again into a little U and a little V, then you will say, okay, it's already U, there is no V, so the result is again U. So projection done twice is the same as projection done once. This is clearly true for the geometrical perspective, and therefore the geometrical definition fulfills this equality here that we call the algebraic definition. The more interesting question is whether that one-liner here in this algebraic definition already gives you all the rich and beauty that we've been talking about before. Okay, so we want to check this equivalence between the two definitions, and this one has been checked already. Now for the second direction, we don't have much to start with, right? All we have is our space X and our projector P that is subject to P squared equals P. So where do we get all the geometry from? Where's our space U coming from? Where's our space V coming from? How do we see it's a direct sum, and what's the complementary projector? All these questions, right? And to find these spaces U and V, let's just look back to our examples up here. So let's say this is our capital X, and then that is the action of our operator P, which in this case is P subscript U. And then if the only thing you know is this blue arrow for every given starting point X, how would you describe to someone what the red space U is? Well, you could say U is the set of all endpoints of those blue arrows. Or more precisely, we could write U is the set of all outputs of your operator PU, or well, we used to call that the image of the operator PU. Can we also describe V in operator language? Yes, we can. We can say V is the set of all points little v with the property that when I project them with my projector PU, because that's what I have, I end up at the origin at 0. So V is the set of all those starting points V whose endpoint after the map PU is the origin. Okay, and that is clearly what we call the kernel of our operator PU. Excellent. Now that was quite an inspiration. Let's take that one right here into our abstract algebraic world. So given the space X in our projector P, let's put a space U equal to the image of P and our space V to the kernel of P. Okay, and then we claim that those sets U and V are subspaces of X, but we can already tick that one because the image is always a subspace of that space here, and the kernel is always a subspace of that space here. And then as a second claim, U and V are complementary spaces of each other in X, which means together in a direct sum they give you the whole space X. Okay, and then as a third claim, we could ask whether or not P is what we call PU before. And if that's the case, then we could certainly ask, what about PV? Okay, and in order to make property 2 a bit easier to prove, we should split it into 2a, which says U and V together give you X as a sum. And then statement B, it's a direct sum, which we know how to check. We just check the intersection, whether or not that's just a zero vector. Okay, one claim down, 3 still to go. Now let's start with claim number 2, and let me start with 2a. So here we have to show that every little x from X can be written as a little u plus a little v from U and V. So let little x be an arbitrary element of capital X. And then let's just write the following. You can write little x as px, which is certainly in the image of P and therefore in U, plus, well, now we have to repair what we just did, so we have to add x and subtract px, and it remains to show that this is, we don't know yet, that this is in V, which is the kernel of P. How do you show that something's in the kernel? Well, you apply P to it and test whether you get 0. So P of this expression here is, well, let's write it out again, P of x minus Px, and then it's of course just Px minus P, Px, but of course instead of P times P we can write P squared, and then here we go, you're using for the first time now our magic equation P equals P squared, and that's why we're getting 0 here. Okay, and that's why not only this first part here is in U, but also this second part here is in V, and we can tick 2A. For 2B, we have to take an element from the intersection of U and V, and we have to show that this can only be the 0 vector. Okay, well, let's start by exploiting the statement that x is in U, which, if you remember correctly, is just the image of P. Well, if x is in the image of P, x can be written as P of something. Well, let's say P of y for some y from our space x. Okay, and now let's exploit the second statement, which is that x is in V, which is the kernel of P, which just means P applied to x gives you the 0 vector. Well, if we bring both of these together, then we get that the 0 vector is P of x, but now x can be replaced by P of y, which gives you P squared of y. But now again, by our projector property, P squared equals P, this is just P applied to y. Well, but then remember that P applied to y is just x. And now look what you've done. X equals 0. So if x is in both U and V at the same time, then it must be the 0 vector. Tick. Okay, now to check claim 3, you have to remind yourselves what the job of that PU was. Well, imagine you split your x into its unique decomposition little u plus little v, and then knowing that these are unique, the pu of x would just be equal to that little u here. Okay, but in our case, I mean, we have exactly this decomposition written underneath. You see that this is px. So indeed, p of u is doing what p is doing. So we can also tick that box. Okay, but then maybe it's equally simple to answer what that is here. So what is pv doing? Well, it's taking your vector x to this vector little v in v here, which in our case is this one. So now we know how we can replace this question mark here. Well, we just have to copy what is written in front of x here. So which operator is applied to your little x here? Maybe it's helping if you squeeze the little identity operator in here, which is of course not changing the statement. Okay, and then you see what goes here. The identity operator minus p is what comes here. And I mean, if you look at this, then I think this is one of the points where you either say mathematics is beautiful or you say what a lot of rubbish. Yeah, decide for yourself what your statement is. We have just seen that this algebraic definition, which is neat and short and easy, gives you just the same as this 20 minutes long geometric definition. Well, if you want, you could ask one question. I mean, we've just seen that I minus P seems to be the geometric kind of projector that we called PV before, and we just saw that geometric projectors are also algebraic projectors. There's no difference. But couldn't we check this more easily? And we can. So if you want to check whether or not I minus P is a projector, you just do the computation. So you just check whether the square of this is again the operator itself. So what do you see? You see I minus P times I minus P, and that is I squared, which is I minus P minus another P plus P squared. Okay, but now that is just I. That, our projector property, is just P. Okay, and now everything cancels and all that remains is I minus P. Isn't that beautiful? I mean, it's not that I don't like geometry, not at all, but isn't it great if you can tell the same story in one line that you've been telling in 20 minutes before? Okay, but of course it's important to see both sides of the coin. Now, since I minus P is just the complementary projector PV of our other projector P equals PU, and since U and V just freely can change roles, we will have the same equations here, but just with image and kernel replaced and P and I minus P replaced. Again, so maybe it's worth writing these separately. So we have that U is on the same time the image of P as well as the kernel of I minus P, and then V is, as we said before, the kernel of P, but just by symmetry it must also be the image of the complementary projection of P. And something else that we didn't say before, P and its complementary projection add up to 1, which is pretty obvious from the complementary projection just being 1 or I minus P. Okay, and maybe one more comment. This is not the first time where algebra beats another subject. I mean, here we've seen that when geometry takes 20 minutes, algebra needs 1 line to say the same. And we had a similar situation in the very first lecture when we introduced the Moore-Penrose inverse, and I've been talking for like 10 minutes about minimizing this norm, and then if that is done, minimizing the other norm. So this is like a optimization problem, or you could motivate it with numerical purposes. Okay, and then comes algebra and writes down what the Moore-Penrose inverse is in just 4 lines, right? So if you forgot, then look back, and then maybe at the end of the course you will also be team algebra. Let's say one more thing about projections. I mean, when you hear about projections for the first time in your first year linear algebra course, then it's always about orthogonal projections, right? So if this is your space U, and this is your element x, then the projection will always act somehow orthogonally to your space U, so that you have a right angle here. But this is your linear algebra course in the first semester. I mean, when we set projections here, we didn't have any right angles, we didn't have scalar products, we didn't even have norms, we just took a vector space and started from there. So there's no, it's just complete syntax error to speak of orthogonality in that general context. I mean, we had situations where the projection takes you down to your space U in maybe that direction. And that was when our complementary space V was facing like this, instead of being orthogonal to you from the very beginning. Okay, so in what we said before, neither in the geometric definition nor in the algebraic definition, there was any kind of orthogonality involved. Good. Now let's come to orthogonal projections. So if you want to speak about orthogonal projections, then you need orthogonality. So you need a scalar product, so you need a Euclidean space, at least, possibly Hilbert space. So in particular, you have your scalar product, and together with the scalar product, you have a norm. Now in this whole geometric setup, you could of course now start by taking two subspaces U and V, where every little U and every little V have a scalar product of 0, so these spaces are orthogonal to each other, and then tell the whole 20-minute story to arrive at a projection that will then be an orthogonal projection. Is there a chance to do the same with your algebraic definition, which just consists of this one line? So how can you plug orthogonality into this equation? Well, also that is possible, and all you have to do is to expect that P is also equal to P star, the adjoint operator, which we've been introducing before, and which exists now because we are now in a Euclidean space. So while this equality guarantees you the projection property, that one will guarantee the orthogonality. Okay, and now of course we should also prove this. Okay, but also that proof is not very difficult. Let's try to do that quickly. So we have to show that if this equation here holds, then our spaces U and V will be orthogonal to one another, and we know how they are connected to P. U is the image of P, and V is the kernel of P, or we could also say the image of the complementary projector. Now let U be an arbitrary element of U, and V be an arbitrary element of V, and we have to show that they are orthogonal to each other. So the scalar product is equal to 0. Let's see how we get there. Okay, because U is in capital U, it is the image of some point under the operator P. Let's call that point little x. Okay, and similarly V is in the image of I minus P. So it's the image of some other point under the operator I minus P. Okay, if we plug these in here, we will now have to use what is given to get us from here to here. Let's start with the adjoint. So we know that we can get this P across the comma by writing P star on the other side. But then, because P star equals P, we can just replace this P star here by P, and then multiply this product out. And then note that by that projector equality, this term here is equal to 0. So indeed we end up with our claim.